Greetings to visitors of my channel. Here is another calculus problem from Putnam 2005. It is required to find all differentiable functions defined for positive x, whose values are also positive. In addition, there must exist a positive real number a, for which this cute equation, where f prime is of course the first derivative of f, holds for any positive x. To me, it appears that the authors of the problem are so much concerned about anything negative that they took all the precautions to ensure that only positive stuff appears in the task. In fact, this requirement of universal positiveness doesn't really simplify the problem, but on the contrary, creates some restrictions. Please pause the video and try to solve the problem on your own. The equation is certainly the most essential part of the conditions, and it has a derivative applied to a dirty argument, a over x. So let's clean the argument by substituting y for a over x. Then x equals a over y. The substitution makes the right-hand side more complex than it was originally. However, now we have a pure argument for the derivative, as this means a lot. Let's replace letter y with x and rewrite the denominator using negative powers, since, as you probably guessed, we are going to differentiate the equation. Power -1 here relates to function f. Placing another pair of brackets around f would reduce readability, while if I place -1 straight after f, it could be misinterpreted as the inverse function. Even though inverse functions are not used in this video, I prefer to avoid this ambiguity. Further on, I will also omit brackets for the power of function, in hope it won't cause any confusion. Note that factor a here is a constant, so we can simplify the differentiation by dividing the equation by a. The derivative of the left-hand side is just the second derivative of f divided by a. Now we need to take a deep breath and find the derivative of the right-hand side. The right-hand side is a product of two factors, so we take the derivative of x to the power of -1, which is negative x to the power of -2, and multiply it by the second factor. Now we need to add the first factor multiplied by the derivative of the second factor. Since the second factor is a complex function, we need to use the chain rule. First, we take the derivative of power -1 and get minus f of a over x to the power of -2. This has to be multiplied by the derivative of function f itself and the derivative of a over x, which is -a times x to the power of -2. Now we can get rid of the argument a over x. We have f of a over x to the power of -1, which can be replaced using the equation for f prime of x. We divide this equation by ax to the power of -1 and find that the value we need to replace is a to the power of -1 times x times f prime of x. So we do the replacement. Further on, we have two minuses giving plus when combined. Then x to the power of -1 times ax to the power of -2 is ax to the power of -3. We also have f of a over x to the power of -2. This is the square of the expression we found before. This means that we have to take each factor squared. Finally, the value of f prime of a over x can be found from the given equation. Now we can move a back to the right-hand side by multiplying the equation by a. Meanwhile, we will simplify the equation. After multiplying by a, the left-hand side becomes just the second derivative of f, In the right hand side we have x to the power of negative 2 times x is x to the power of negative 1. A to the power of negative 1 times a coming from the denominator is a to the power of 0. So a disappears and we get just x to the power of negative 1 times f prime of x as the first right hand side term. In the second term, x to the power of negative 3 times x squared times x gives x to the power of 0, meaning that there will be no x. Then a times a to the power of negative 2 times a from the left hand side gives a to the power of 0. So a also goes. And the second term is just f prime of x squared times f of x to the power of negative 1. That's a surprise, isn't it? We just wanted to get rid of argument a over x, but we actually removed parameter a completely and are left with a differential equation for f. Let's see if we can solve it. To start with, we can forget about the negative powers and rewrite the right-hand side in a more convenient way. Then we can get rid of the denominators by multiplying both sides by x times f of x. Now we can clear the screen and copy the obtained equation to the top, meanwhile moving the right-hand side terms to the left by changing their signs. Let's introduce notation y equals f of x. That allows rewriting the equation in a more compact way. This is a second-order differential equation as the second derivative is present there. It is not homogeneous and not even linear as it has y prime squared. No standard methods apply here apart from one, reducing the order. If we somehow can express the whole left-hand side as a derivative of something, we can write that this something is a constant, reducing the equation to a first-order differential equation, which is much more convenient to deal with. We have a formula for the derivative of a product, giving two terms for the derivative, while our expression has three terms. Let's make two terms out of three by grouping first two terms and factoring out y. Look at the expression in the brackets. Doesn't it tell you something? The expression in the brackets is just the derivative of x, y prime. Indeed, if we assume u to be x and v to be the first derivative of y, then u prime v is y prime, which is exactly the second term in the brackets, while u v prime is x times the second derivative of y, which matches the first term in the brackets. And we need to copy the remaining part of the equation. So we copy y, while the last term can be rewritten as xy prime times y prime. Again, we've got something ringing a bell, however, with a minor but significant difference. If we had plus instead of minus, we could take xy prime for u and y for v and represent the left-hand side as the derivative of u times v. However, with minus instead of plus, the formula for uv prime doesn't apply. Any suggestions? Fortunately, there is also a formula for the derivative of a fraction, containing the minus we need. To apply the formula, we need v squared in the denominator, and we can get it dividing the expression by v squared. In our case, v is y, and y is f of x, which is positive according to the conditions. This means that y squared is non-zero, and we can divide both sides of the equation by y squared. Now the left hand side is the derivative of xy prime over y, and it equals 0. This means that xy prime over y must be a constant, name it k. We've got a first order differential equation with separated variables, which means that all our troubles are left behind. Let's again clear the page and solve the equation. At start, we move x to the right hand side by dividing both parts of the equation by x. Note that x is positive and therefore non-zero. The left hand side of the equation is the derivative of logarithm of modulus y, while the right hand side is the derivative of k times logarithm of the modulus of x. Since, according to the conditions, both x and y are positive, we can remove moduli, and let's also place k inside the logarithm as the exponent. Since the functions have same derivative, they differ by a constant, name it C capital. Now we've got two constants, which is expected given that a second order differential equation should have two constants in the solution. In order to get the expression for y, we exponentiate the equation. The left hand side of the new equation is just y. E to the power of c is a new constant, name it c small, and it is positive as a power of e. The first term in the right hand side is x to the power of k. Now we can write that the function we are looking for, f of x, is c times x to the power of k, where c is a positive constant. This condition is necessary but may be insufficient, as a positive a mentioned in the conditions is not guaranteed to exist. Let's see for which values of c and k the value of a can be found. So the first derivative of x is k times c times x to the power of k minus 1. And we can write the expression for f prime of a over x, which is the left-hand side of the equation we need to satisfy. We also need the expression for the right-hand side of the equation, so we get a fraction which can be reduced by x. And we equate the expressions for left and right sides. Here x's are cancelled out, which is great, because we need the equation to hold for any positive x. Now, since the right hand side is positive, so must be the left hand side. Therefore, k must be positive. Let's write that k is greater than 0 and divide both sides of the equation by k times c. We've got an equation for a, and if k is different from 1, we can find the value of a as 1 over kc squared, or to the power of 1 over k minus 1, or kc squared, or to the power of 1 over 1 minus k. Since kc squared is positive, the value of a exists and it is unique. So let's write down that if k is not equal to 1, the value of a exists for any positive c and it is unique. And we need to consider the case k equals 1. Now the exponent of the left hand side is 0, so the left hand side turns into 1, while the right hand side is 1 over c squared. Now the equation is void of a, which means the condition will hold for any positive a. Here c squared must be 1, and since c is positive, it can be only 1. Let's again remove few lines and write that when k equals 1, c must be 1, while a may be any positive number. Indeed, when both k and c are equal to 1, then f of x is just x. Therefore, f prime of x is a constant equal to 1, so f prime of a over x is 1 for any positive x and a. And the right hand side is 1 as well for any positive x. Finally, we are ready to write the answer, which consists of two branches. F of x equals c times x to the power of k, where c is any positive number, while k is a positive number different from 1. The second branch is just f of x equals x. Thanks to all who were patient enough to watch this video till the end.